Hello and welcome back. Let us try to understand an important concept in linear algebra, the eigenvectors and eigenvalues. In German, eigen means a specific of. So we are going to extract the specific details of a matrix by decomposing it into eigenvectors and eigenvalues. So this technique is used in principal component analysis. And this is the basis for singular value decomposition, another linear algebraic concept. So both eigenvectors, eigenvalues and singular value decomposition both are used to decompose a matrix into two matrices where we are trying to extract the specific behavior of the matrix. If you take A as a matrix and X as an eigenvector and lambda is an eigenvalue is a scalar, X, the eigenvector, is a vector. When you multiply your matrix with A, your matrix A with the eigenvector and you multiply a constant with eigenvector, you will get the same value. It means the left hand side and right hand side both are going to be equal. That means they are equal. So you can decompose a matrix into eigenvectors and eigenvalues. How? We will see it in a moment. But the eigenvectors, eigenvalues concept can be applied on a square matrix only. The dimensionality should be always n by n. 2 by 2, 3 by 3, 4 by 4, n by n, right? An eigenvalue, eigenvector decomposition can be done on a square matrix only. The eigenvectors explain you the specific behavior of the matrix A and eigenvalues quantify the behavior of each vector. So we'll see that in detail in coming session. So before we jump into math, let us look at a little bit of theory here. The eigenvectors and eigenvalues are also referred to as characteristic vectors, latent roots, or characteristic equations. So in German, eigen means a specific of or characteristic of. So we are trying to decompose our original matrix A into eigenvectors and eigenvalues such that the behavior, the specific characteristics of the matrix will be extracted from the matrix. So if you take the principal component analysis an example, in principal component analysis we calculate or we derive the covariance matrix and then try to decompose the covariance matrix into eigenvectors and eigenvalues, which is nothing but the covariance in the data we are trying to extract. So if you pass normal data set, it is not going to work because data set is not going to be n by n matrix. It's not going to be a square matrix. That's first problem. The second thing is there should be some behavior to the matrix, and when you apply eigenvalues, eigenvectors, the eigenvectors are going to extract the essence from the data set or the specific behavior of the data set. So if you calculate the covariance matrix, that's going to be a square matrix. And on top of it, you apply eigenvalues, eigenvectors, you will get the essence, the covariance residing in the dataset. So that is one example, right? So you call, generally eigenvalues are called as spectrum also. Eigenvalues of a matrix is also called as, it's a spectrum, okay? Eigenvectors and eigenvalues are vectors and numbers associated to a square matrix. I just told you. The matrix must be n by n matrix, a square matrix, rather eigenvalues, eigenvectors decomposition cannot be done, okay, associated to a square matrix, and together they provide eigen decomposition of matrix which analyzes the structure of the matrix. Eigen decomposition we call it as, okay. So we'll see what it is and how to do it in a moment. So I have taken a matrix, a simple 2 by 2 matrix. If you understand what is eigenvalues, eigenvectors, that's enough. You no need to be a PhD in eigenvalues and eigenvectors to know or learn machine learning and deep learning. Okay. So I have taken a two-dimensional matrix, right, 5, 1, 3, 3, and then I decomposed this matrix into eigenvalues and eigenvectors. So I have x1, 1, 1, a vector, and lambda 1, 6, a value, and x2, 1 minus 3, a vector, and lambda 2, is equal to 2. That is a eigenvalue. So an n by n matrix can have n number of eigenvectors and eigenvalues, maximum n number of eigenvalues and eigenvectors. So here it's a 2 by 2 matrix, and we have got two eigenvectors x1 and x2, two eigenvalues lambda 1, lambda 2. I said ax is equal to lambda x, right? When you multiply your original matrix A with a vector and your vector multiplied with a constant, you will get the same value. Let us see that. So I have taken this A 5 1 3 3 and this 1 1, the eigenvector, I multiplied, I have got 6 6, a vector, and I multiplied 6 with 1 1, I got 6 6. So the right hand sides of these equations are equal, so left hand sides are equal. So ax is equal to lambda x. So I can say x1 is an eigenvector of the matrix 5 1 3 3. 6 is an eigenvalue of the matrix 5 1 3 3. Similarly, I found another eigenvector and another eigenvalue. If you multiply 1 minus 3 with the matrix, I got 2 minus 6, and if I multiply lambda 2 with 1 minus 3, I have got 2 minus 6. So right hand sides are equal, left hand sides are equal. So I have got ax2 is equal to lambda x2. So x2 is also an eigenvector and lambda 2 is an eigenvalue. So you can represent, or you can actually decompose your A matrix into an eigenvalue matrix and an eigenvector matrix. Okay, so you decomposed. So this matrix is decomposed into eigenvector matrix. I actually kept the x1 and x2 next to each other and created a matrix 1 1 3 minus 3 and eigen values matrix. Eigenvalues matrix is always a diagonal matrix. When I say diagonal matrix, there will be values in the diagonal. All off diagonal values are going to be 0. So if you see this, lambda 1 and lambda 2, off diagonal values are 0. So I can represent it as 6 0 0 2. So the A can be decomposed into 1 1 1 minus 3 and 6 0 0 2. So this is eigenvalue decomposition, we call it. This matrix is decomposed into two matrices. So now I can say the 1 1 vector and 1 minus 3 vector are actually have extracted the essence in the data or specific behavior of the matrix A, and the 6 and 2 are the signifying factors, or the quantifying that 1 1 vector extracted 6 quantity. What is that quantity? We'll see in a moment. When we do PCA, we'll see what is the quantity. So 6 quantity it extracted, 6 quantity of the specific behavior of the A matrix it extracted, and 1 minus 3 extracted 2. When you compare these two vectors, right, 1 1 vector, the first vector has extracted more essence from the data set than the second matrix. So we'll see in PCA what is that extract. So we can say AV is equal to V lambda. What is V? V is the eigenvector matrix. Lambda is the eigenvalue matrix. It's a diagonal matrix. So when you multiply A and V, you get some matrix. When you multiply lambda and V, it's a V and lambda. So it's a lambda is a capital lambda. This is small lambda. And when you multiply V with the capital lambda, you got the same thing. That means AV is equal to V lambda. That's a proven thing. So your A can be decomposed as V lambda V inverse. If you multiply with A inverse on both sides, V inverse becomes I. So A into I is equal to A. So A is equal to V lambda V inverse. So a matrix A can be eigen decomposed into V lambda V inverse. Okay. So we can find these eigenvalues and eigenvectors. How can we find it? We'll see it in next session. The point here is that when a matrix can be multiplied with a vector and the same vector can be multiplied with a scalar, a constant, if you get the same value, then x can be called as eigenvector and lambda can be called as eigenvalue. Eigenvector extracts the essence, the eigen decomposition of your matrix extracts the essence from the data, and the eigenvalue specifies the quantifies the essence, how much essence the eigenvector extracted from A. So if you see this matrix is decomposed into two eigenvectors and two eigenvalues. An n by n matrix can have maximum n number of eigenvectors and n number of eigenvalues. An eigenvector, after deriving eigenvectors, you can represent eigenvectors, combine all eigenvectors and represent it as a eigenvector matrix, and combine all eigenvalues in a diagonal matrix and specify it as eigenvalue matrix. And you can say that AB is equal to V lambda. Your original matrix multiplied by eigenvector matrix is equal to your vector matrix multiplied with eigenvalue matrix. So, or in other words, right, you can say A can be decomposed as V lambda V inverse. This is called as eigenvalue decomposition. How to do it? We'll see it in a moment with a simple example. Thank you.